Hello there, and welcome to the Sleepy Science Society. Tonight, we're drifting into one of the most beautiful mysteries that nature has ever revealed to us. A phenomenon so strange that even Albert Einstein refused to believe it could be real. A connection so profound that it links particles across the entire breadth of the universe. We're exploring quantum entanglement. And if you find these gentle journeys into science as fascinating as I do, I invite you to like and subscribe. It helps others discover this quiet corner where science meets wonder, one sleepy soul at a time. But for now, all you need to do is settle in. Let your breathing slow. Allow your mind to soften into curiosity. Tonight, we're venturing into a realm where the rules of everyday reality dissolve into something far stranger and more wondrous. We're exploring a place where two particles, separated by billions of miles, can remain connected in ways that seem to defy every law of physics we thought we understood. We're discovering how the universe, at its deepest level, might not be made of separate, independent things at all, but rather a single, interconnected whole where everything touches everything else in invisible ways. Picture this moment. You're resting somewhere comfortable, perhaps in bed, perhaps in a favorite chair. The room around you feels solid and separate. The walls contain a space that feels distinctly yours. The air between you and the nearest star seems like an unbridgeable void, empty and vast. Our everyday experience teaches us that things are separate, that influence requires a contact or at least some signal passing through the space between. When you push a door, your hand touches it directly. When you call a friend, sound waves or electromagnetic signals carry your voice across the distance. Nothing happens without something traveling from here to there. This intuition about separateness runs deep in human thought. It shapes how we build our understanding of cause and effect, how we think about identity and individuality, how we construct our models of physics and philosophy. For thousands of years, thinkers assumed that the universe was made of distinct, separate things, each with its own properties, influencing each other only through local interactions that respect the finite speed at which information can travel. Then came quantum mechanics, and with it, the revelation that this picture, while useful at human scales, breaks down when you examine the universe closely. At the level of atoms and subatomic particles, the rules shift. Boundaries blur. The very concept of separate, independent objects becomes questionable. And nowhere is this more dramatically demonstrated than in quantum entanglement, where particles that have interacted once remain connected forever, no matter how far apart they drift, responding to measurements in coordinated ways that no classical theory can explain. Quantum entanglement sits at the heart of what makes quantum mechanics so peculiar and so powerful. It represents a type of connection that has no equivalent in our everyday world. Imagine two dancers, spinning on opposite sides of the earth. Now imagine that when one dancer pirouettes to the left, the other, without any signal passing between them, instantly spins to the right. Not because they planned it, not because they're following the same choreography, but because they are, in some fundamental way, parts of a single dance that transcends space itself. This is the essence of entanglement, and it's not science fiction. It's science fact, proven in laboratories around the world, and now forming the foundation of revolutionary new technologies that will reshape our future. As you rest there in the darkness, know that the particles making up your body, the atoms in the air you breathe, may have been entangled with particles now scattered across the cosmos. The quantum world doesn't respect the boundaries we imagine. It doesn't care about distance or separation. At the smallest scales, reality operates according to rules that seem almost magical. Yet they are precisely what allows the universe to exist as it does. Tonight, we'll unravel this mystery together, slowly and gently, discovering how entanglement was found, what it means, and why it might be one of the most important discoveries in the entire history of science. The foundation, understanding the quantum realm. Before we can truly appreciate the strangeness of quantum entanglement, we need to understand the world in which it lives. The quantum realm is the domain of the very small, the world of atoms and subatomic particles, where the physics we learned in school simply stops working. Down at these microscopic scales, reality becomes probabilistic rather than deterministic. Particles don't have definite positions or speeds until we measure them. They exist instead in what physicists call a superposition, a kind of ghostly state where they inhabit multiple possibilities simultaneously. Think about a coin spinning in the air. While it's spinning, it's neither heads nor tails. It's both at once, a blur of possibility. In classical physics, we understand that the coin really is one or the other. We just don't know which until it lands. But quantum mechanics tells us something far stranger. At the quantum level, particles actually exist in this state of being multiple things at once. An electron can spin both clockwise and counterclockwise simultaneously. A photon, a particle of light, can travel through two different paths at the same time. This isn't a limitation of our knowledge. This is the actual nature of reality at the smallest scales. To truly grasp how radical this is, we need to appreciate what came before. Classical physics, the physics of Newton and Maxwell, painted a picture of a clockwork universe. Every particle had a definite position and velocity at every moment. If you knew the exact state of the universe at one time and you understood all the forces at work, you could in principle calculate the exact state at any future time. The universe was deterministic, predictable, mechanical. Randomness and probability were just reflections of our ignorance. The dice roll might seem random, but if you knew the exact angle, the exact force, the exact surface texture, you could predict which number would come up. Quantum mechanics shattered this picture completely. In the first decades of the 20th century, physicists studying atoms and light encountered phenomena that classical physics couldn't explain. Atoms emit light at specific frequencies, creating discrete lines in their spectra rather than a continuous rainbow. When you shine light on metal, it ejects electrons, but the energy of those electrons depends on the color of the light, not its brightness. Particles of light behave like waves, creating interference patterns. Waves behave like particles. arriving in discrete chunks rather than continuous flows. All these puzzles came together in the mid-1920s when a group of brilliant young physicists, working mostly in Germany and Denmark, developed quantum mechanics. Werner Heisenberg formulated one version using matrices and abstract algebra. Erwin Schrödinger developed another using wave equations. Max Born interpreted the waves as waves of probability. Paul Dirac unified the approaches into a comprehensive mathematical framework. And Niels Bohr, the elder statesman, led the philosophical interpretation that came to be called the Copenhagen interpretation. This principle, called quantum superposition, was demonstrated most famously in the double-slit experiment. When scientists fire individual photons or electrons at a screen with two slits, something extraordinary happens. Each particle somehow passes through both slits at once, interfering with itself to create a pattern on the detector behind the slits. The pattern that appears is not what you'd get if particles were little balls taking one path or the other. It's an interference pattern, the kind of pattern you see when waves overlap and combine. The particle is behaving as a wave, spread out in space, existing in multiple places until the moment of measurement. Let's linger on this experiment because it captures so much of quantum weirdness. Imagine you have a source that fires single electrons, one at a time, toward a barrier with two narrow slits. Behind the barrier is a detection screen that lights up wherever an electron hits it. You might expect that electrons, being particles, would go through one slit or the other, creating two bright bands on the screen corresponding to the two paths. But that's not what happens. Instead, as electrons accumulate on the screen over time, they form a pattern of alternating bright and dark bands, an interference pattern. This is what you'd expect from waves. When waves pass through two slits, they spread out and overlap on the far side. Where the peaks of the two waves align, they reinforce each other, creating bright spots. Where a peak meets a trough, they cancel out, creating dark spots. But electrons are particles, tiny localized objects. How can a single electron interfere with itself? The answer quantum mechanics gives is that the electron doesn't go through one slit or the other. It goes through both, existing in a superposition of paths. Its wave function, the mathematical description of its quantum state, passes through both slits and interferes with itself. When the electron hits the screen, the wave function collapses, and the electron is detected at a specific point. But which point is likely is determined by the interference pattern, by the combined wave that came through both slits. Here's where it gets even stranger. If you try to determine which slit the electron actually went through by placing a detector at one of the slits, the interference pattern disappears. When you observe which path the electron takes, it stops behaving like a wave spread through both slits and starts behaving like a particle taking one definite path. The act of measurement fundamentally changes the system. It forces the electron to choose, collapsing its superposition into a definite state. When we do measure a quantum particle, when we actually look to see which slit it went through, the superposition collapses. The particle is forced to choose, to become one definite thing in one definite place. This act of observation fundamentally changes the system. It's as if reality itself is undecided until someone pays attention. This leads to philosophical puzzles that have troubled physicists for nearly a century. What counts as an observation? Does consciousness play a role? How can the act of measurement create reality? The quantum world operates on probabilities. We can't say for certain where an electron will be found, only where it's likely to be. We can calculate these probabilities with stunning precision. Quantum mechanics is the most accurately tested theory in all of physics. Its predictions have been confirmed to extraordinary decimal places. Every piece of modern technology, from computer chips to MRI scanners to LED lights, depends on our understanding of quantum mechanics. Yet despite this practical success, the theory itself describes a world that seems almost impossible to believe. Consider the precision of these predictions. Quantum electrodynamics, the quantum theory of how light and matter interact, predicts a property of the electron called the magnetic moment to better than 1 part in a trillion. Imagine measuring the distance from New York to Los Angeles and being accurate to within the width of a human hair. That's the level of agreement between theory and experiment. No other scientific theory comes close to this accuracy. Quantum mechanics works extraordinarily well. Particles at the quantum level are described by something called a wave function. This is a mathematical object, a kind of field of possibility that spreads throughout space. The wave function contains all the information about where a particle might be, what momentum it might have, what state it might be in. When you make a measurement, you don't just discover pre-existing properties. You collapse the wave function, forcing nature to select one outcome from many possibilities. The mathematics works perfectly. But what it's telling us about the nature of reality remains deeply mysterious. Think of the wave function as a cloud of possibility hovering over space. The cloud is denser in some regions, fainter in others. The density at each point tells you the probability of finding the particle there if you look. Before you measure, the particle isn't secretly hiding at one particular spot in the cloud. It genuinely exists everywhere the wave function is non-zero, in a state of quantum superposition. Only when you perform a measurement does the cloud suddenly collapse to a single point, giving a definite answer. Werner Heisenberg, one of the founders of quantum mechanics, discovered that there are fundamental limits to what we can know. His uncertainty principle states that you cannot simultaneously know both the precise position and the precise momentum of a particle. The more accurately you measure one, the less you can know about the other. This isn't a technical limitation. It's not about building better instruments. It's a fundamental feature of reality itself. At the quantum level, particles don't have both a definite position and a definite momentum. These properties are genuinely uncertain until measured. The uncertainty principle emerges from the wave nature of particles. A wave that's tightly localized, confined to a small region of space, must contain a wide range of frequencies to create that localization. Since momentum is related to wavelength, a particle with a well-defined position necessarily has an uncertain momentum. Conversely, A particle with a definite momentum has a wave function that's spread out over space, making its position uncertain. This is a mathematical property of waves, but quantum mechanics says it applies to matter itself. Another founding figure, Niels Bohr, emphasized that quantum mechanics requires us to abandon our classical intuitions. The questions we ask determine what kind of answers we can get. A particle isn't secretly traveling one path or the other through the double slits. It's not secretly spinning in one direction or the other. These properties simply don't exist in a definite state until we measure them. Bohr called this complementarity, the idea that different experimental arrangements reveal different complementary aspects of reality, and we cannot observe all aspects simultaneously. Bohr's philosophy went deeper. He argued that we can't meaningfully talk about quantum objects independent of how we observe them. The apparatus we use, the type of measurement we perform, becomes part of the phenomenon we're studying. There's no objective reality separate from our means of observing it. This position was controversial and remains debated. Some physicists found it too radical, too dismissive of the idea that nature has properties independent of our knowledge. This quantum foundation, as strange as it seems, has been verified countless times. Experiments have shown that individual atoms can be in two places at once. They've demonstrated that particles can tunnel through barriers that classical physics says they shouldn't be able to penetrate. They've revealed that the quantum world is genuinely probabilistic, not just apparently so because of our ignorance. And it's in this weird quantum realm where superposition reigns and measurement creates reality, that entanglement emerges as perhaps the strangest phenomenon of all. Quantum tunneling, for instance, allows particles to pass through energy barriers that they classically shouldn't have enough energy to surmount. Imagine rolling a ball toward a hill. If the ball doesn't have enough energy, it rolls partway up and then back down. But a quantum particle, described by a wave function that extends through space, has some probability of appearing on the far side of the barrier, as if it tunneled through. This effect is crucial in nuclear fusion, allowing protons to overcome their electrical repulsion and fuse together in the cores of stars. It's also the basis of technologies like scanning tunneling microscopes, which can image individual atoms on surfaces. The quantum world is not a minor correction to classical physics, a slight tweak needed to get the details right. It's a fundamentally different reality, operating on principles that contradict our deepest intuitions about how things work. Objects don't have definite properties until observed. Particles can be in multiple states simultaneously. The act of measurement creates the reality we see. And, as we're about to explore, particles can be connected across vast distances in ways that Einstein called spooky, but which we now recognize as one of nature's most profound truths. The birth of a paradox, Einstein's challenge. The story of quantum entanglement begins with skepticism, with resistance, with one of the greatest minds in physics refusing to accept what the mathematics seemed to be saying. In the early 1930s, quantum mechanics was still young, its implications still being worked out. The theory had achieved remarkable successes explaining atomic structure, the behavior of light, and phenomena that classical physics couldn't touch. But Albert Einstein, who had helped birth quantum theory with his explanation of the photoelectric effect back in 1905, grew increasingly uncomfortable with where the theory was heading. Einstein's own contributions to quantum theory were fundamental and ironic. His explanation of the photoelectric effect, for which he received the Nobel Prize in 1921, proposed that light comes in discrete packets of energy called photons. This particle nature of light was revolutionary, helping establish quantum theory's foundations. Yet, as the theory developed through the 1920s, incorporating wave-particle duality, uncertainty, and probability, Einstein found himself disturbed by the implications. The young physicists developing quantum mechanics, particularly those gathered around Niels Bohr in Copenhagen, embraced the weirdness. They accepted that particles don't have definite properties until measured, that observers play an essential role in creating reality, that nature is fundamentally probabilistic rather than deterministic. For them, these strange features weren't problems to be solved but truths to be accepted. Quantum mechanics was complete as it stood, even if its picture of reality seemed bizarre. Einstein believed in what philosophers call local realism. Local means that objects are only directly influenced by their immediate surroundings. An action though here can't instantly affect something far away without some signal traveling between them, and that signal can't travel faster than light. Realism means that objects have definite properties whether or not we're observing them. A particle has a real position and a real momentum, even if we don't measure them. These principles seem to like common sense, the bedrock of any sensible physics. The locality principle was particularly important to Einstein because it followed from his own theory of relativity. Special relativity, published in 1905, established that nothing can travel faster than light, that simultaneity is relative, and that cause and effect have a maximum speed of propagation. Information can't leap instantaneously from one place to another. If it could, you could arrange situations where effects precede their causes, leading to paradoxes that would tear apart the logical structure of physics. But quantum mechanics, particularly as interpreted by Bohr and his colleagues in Copenhagen, appeared to violate both principles. It said that particles don't have definite properties until measured. It described measurements on distant particles that seemed to be mysteriously coordinated. Einstein found this deeply troubling. In letters to friends, he expressed his discomfort with a theory that made reality dependent on observation. He famously wrote, "I like to think the moon is there even when I'm not looking at it." The debates between Einstein and Bohr became legendary in physics history. They would meet at conferences and engage in intense discussions that stretched late into the night. Einstein would devise thought experiments meant to show contradictions or absurdities in quantum mechanics. Bohr would carefully analyze each scenario, showing how quantum mechanics consistently handled the situation, even if the result seemed strange. These exchanges sharpened both men's thinking and helped clarify the conceptual foundations of quantum theory, even though they rarely changed each other's minds. In 1935, Einstein collaborated with two younger colleagues, Boris Podolsky and Nathan Rosen, to publish a paper that would haunt quantum physics for decades. The paper, titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" described a thought experiment, now known as the EPR paradox after the initials of its authors. The EPR argument was elegant and deeply challenging. It considered what happens when two particles interact and then fly apart in opposite directions. According to quantum mechanics, you could set up the situation so that certain properties of the particles remain correlated. For instance, their spins might be opposite. Let's walk through the EPR argument carefully, because it captures Einstein's deepest concerns about quantum mechanics. Imagine a source that creates pairs of particles. These particles interact briefly and then fly apart in opposite directions. Because of conservation laws, certain properties of the two particles are correlated. For example, if they started from a system with total spin 0, then if one particle has spin up along some axis, the other must have spin down along that axis to conserve the total spin. Here's where it gets interesting. Quantum mechanics says that before measurement, neither particle has a definite spin. They exist in superposition, simultaneously spinning both ways. But if you measure one particle and find it spinning, say, clockwise, then you instantly know the other must be spinning counterclockwise, even if it's on the other side of the galaxy. The act of measuring one particle seems to instantaneously determine the state of the other, faster than any signal could travel between them. Now, you could measure the spin along different axes. If you choose to measure one particle's spin along the vertical axis, quantum mechanics says this measurement instantaneously determines what measurement of the other particle along the vertical axis would yield. But you could also choose to measure along a horizontal axis, and making that choice seems to instantaneously determine what a horizontal measurement on the distant particle would yield. Your free choice of which measurement to make on your particle appears to instantly affect which property becomes real for the distant particle. Einstein, Podolsky, and Rosen argued that this presents a dilemma. Either information is traveling faster than light, which violates relativity, or the particles actually had these definite properties all along, hidden from us until measurement reveals them. If the latter is true, then quantum mechanics is incomplete. There must be hidden variables, properties that particles carry with them, that determine in advance what the measurement results will be. The randomness of quantum mechanics, Einstein argued, is just ignorance of these hidden variables, not fundamental indeterminacy. The EPR paper proposed a criterion for what should count as an element of reality. If you can predict a property of a system with certainty without disturbing that system, then that property corresponds to something real. In the EPR scenario, once you measure one particle, you can predict the other particle's property with certainty, and since the particles are far apart, your measurement on one doesn't disturb the other. Therefore, the property of the second particle must have been real before you measured the first. But quantum mechanics doesn't assign a definite value to that property before measurement. So, quantum mechanics must be incomplete. This argument was meant to show that quantum mechanics, while accurate as far as it goes, must be missing something. There must be a deeper, more complete theory underneath it, one that restores realism and locality. Einstein couldn't believe that nature would be so unreasonable as to allow distant events to influence each other instantaneously. He described this apparent feature of quantum mechanics as spooky action at a distance, a phrase that has echoed through physics ever since. The German term he used, spukhafte Fernwirkung, carries connotations of ghostliness, eeriness, something that seems supernatural rather than scientific. Niels Bohr responded to the EPR paper within months, but his response was subtle and philosophical, focused on what we can and cannot say about quantum systems. Bohr argued that we cannot separate the quantum system from the measurement apparatus. The particles don't have independent reality apart from the context of measurement. When you choose to measure one particle's spin along a certain axis, you are creating a complete experimental arrangement that includes both particles, even though they're far apart. The measurement results from this whole setup, not just from properties of individual particles. Bohr's response, while deeply considered, didn't convince everyone. Many physicists found it obscure, difficult to follow. Bohr's prose was notoriously dense. His arguments intertwined with philosophical considerations about the meaning of knowledge and the role of classical concepts in quantum theory. For many years, the EPR paper stood as a profound challenge to the Copenhagen interpretation of quantum mechanics, even if most physicists simply got on with using the theory for practical calculations. What Einstein had stumbled upon, though he didn't know it at the time, was quantum entanglement. The correlation between distant particles that seemed so troubling to him is now understood to be a real feature of nature, not a defect in the theory. But proving that required waiting for new ideas and new experiments. For nearly 30 years, the EPR paradox remained a philosophical puzzle, discussed in seminars but generally considered beyond the reach of experimental testing. Most physicists simply got on with using quantum mechanics, which worked brilliantly for practical problems, and avoided worrying too much about its deeper meaning. Einstein never accepted quantum mechanics as the final word. Until his death in 1955, he continued to believe that a more complete theory would eventually replace quantum mechanics, one that restored determinism and local realism. He worked on unified field theories, trying to bring together gravity and electromagnetism in classical frameworks that might subsume quantum effects. These efforts didn't succeed, and today they're seen as dead ends. But Einstein's critiques of quantum mechanics weren't wasted effort. They forced physicists to think more carefully about what the theory means, what it assumes, and what it predicts. The questions Einstein raised wouldn't go away. They nagged at thoughtful physicists, suggesting that something profound about the nature of reality remained unresolved. The particles in the EPR thought experiment are what we now call entangled. Their quantum states are linked in such a way that you cannot fully describe one without describing the other. They form a single quantum system, even when separated by vast distances. And Einstein's discomfort with this idea would turn out to be the starting point for one of the most important developments in 20th century physics. It's worth noting that Einstein and Bohr, despite their disagreements, remained friends and respected each other deeply. Their debates weren't acrimonious. They were genuine attempts to understand nature, carried out with intellectual honesty, and mutual admiration. Both were trying to make sense of a world that seemed to resist sensible interpretation. That they reached different conclusions speaks to the genuine difficulty of interpreting quantum mechanics, a difficulty that persists today even as the theory has proven itself again and again in experiment. What entanglement really is. To understand quantum entanglement, we need to look more carefully at what it means for particles to be connected in this strange way. When two particles interact at the quantum level, they can become entangled, which means their quantum states are no longer independent. Instead of having two separate wave functions, one for each particle, you have a single joint wave function that describes both particles together as one system. You cannot fully describe the state of one particle without referring to the state of the other. They have become, in a very real sense, parts of a greater whole. The mathematics behind this is elegant and precise, even if the physical meaning remains mysterious. In quantum mechanics, a system's state is represented by a wave function, typically denoted by the Greek letter psi. For a single particle, this wave function depends on properties like position and spin. For two particles, you might naively expect the wave function to be a product of two individual wave functions, one for each particle. And indeed, some two-particle states have this form. These are called separable states, and they represent particles that aren't entangled, that remain independent. But many states cannot be written as products of individual wave functions. These non-separable states are entangled. The wave function describes both particles together in a way that cannot be decomposed into separate descriptions of each particle individually. Information about the two-particle system cannot be reduced to information about each particle on its own. This mathematical non-separability translates into the physical phenomenon of entanglement, where measuring one particle tells you something about the other, even across vast distances. Let's consider a concrete example, the kind that physicists actually create in laboratories. Start with a single photon, a particle of light, with a particular amount of energy. Using special crystals, often made of materials like beta barium borate, you can split this photon into two lower energy photons through a process called parametric down conversion. The crystal's structure and properties, combined with conservation laws, ensure that the two resulting photons are entangled. Their properties are correlated in specific ways determined by the original photon and the fundamental conservation laws of physics. The beauty of using photons for entanglement experiments is that they're relatively easy to create, manipulate, and detect. They travel at the speed of light, allowing you to quickly separate them by large distances. They don't strongly interact with the environment at room temperature, so entanglement can persist longer than with many other particles. And they can be sent through optical fibers or through the air, making them perfect for quantum communication applications. One particularly useful type of entanglement involves what's called the polarization of light. Light waves oscillate, and the direction of that oscillation is the polarization. Imagine a wave on a rope. If you shake the rope up and down, you create vertical waves. If you shake it side to side, you create horizontal waves. Light works similarly, though the oscillation is in electric and magnetic fields rather than physical displacement. A photon can be vertically polarized, horizontally polarized, diagonally polarized, or in quantum superposition of these states. When you create an entangled pair of photons through down conversion, you can arrange the process so that their polarizations are linked in specific ways. For instance, you might create pairs where if you measure one photon and find it vertically polarized, the other will be horizontally polarized, and vice versa. Or you might create pairs where both photons always have the same polarization. The correlation depends on the details of how you create the entangled state, but once created, the correlation is locked in. Here's the crucial, mind-bending part. Before you measure, neither photon has a definite polarization. They each exist in a superposition of vertical and horizontal, but they're not in superposition independently. The pair exists in a shared quantum state where the possibilities are entangled. It's not that one photon is definitely vertical and the other definitely horizontal, and we just don't know which is which. Rather, the system exists in a state where the correlation is definite, but the individual results are not. Imagine two coins, but instead of normal coins, these are quantum coins. Before you look at either one, neither is heads or tails. Each is in superposition, simultaneously both. But they're entangled such that if one turns out to be heads when you look, you know the other will be tails. The correlation between them is perfect and predetermined by their shared quantum state. Yet, which specific outcome you'll get for either coin, heads, or tails is completely random. This combination of perfect correlation and fundamental randomness is what makes entanglement so strange and so powerful. When you finally do measure one photon, you force it to collapse into a definite state, say, vertical. At that instant, even if the other photon is miles away, light years away, on the other side of the universe, it too collapses into the correlated state, in this case, horizontal. The measurement of one particle seems to instantaneously affect the other. Einstein called this spooky because it appears to involve faster-than-light influence. How can measuring a photon here immediately determine the state of a photon there, with no time for a signal to pass between them? The answer, physicists now understand, is subtle and requires careful thought. While the correlation is instantaneous, you cannot use it to send information faster than light. Here's why. The result of your measurement is random. You can't control whether you'll get vertical or horizontal. When you measure your photon, you get a result, let's say vertical. You now know your colleague measuring the distant photon will get horizontal. But you have no way to force your result to be vertical rather than horizontal. You can't encode a message in the measurement outcomes because you don't control those outcomes. They're genuinely random. Your colleague, measuring their photon, sees a random sequence of vertical and horizontal results. Only when you later communicate classically, at or below the speed of light, comparing notes about what you both measured, do you discover the perfect correlations. The entanglement is there. real and immediate. But it doesn't allow faster-than-light messaging because the randomness prevents you from controlling what information the correlation carries. The statistical patterns reveal the entanglement, but individual measurements just look random. What entanglement does violate is local realism, the combined assumption that particles have definite properties independent of measurement, and that distant events can't instantaneously influence each other. The particles don't secretly have these properties all along, as Einstein hoped with his hidden variables. The correlations are stronger than any local hidden variable theory can explain. This isn't just a theoretical claim. It's been tested in experiments and proven to be true, as we'll explore in detail when we discuss Bell's theorem. Nature really is this strange, and we have the experimental evidence to prove it. Another way to think about entanglement is through the concept of quantum information. In classical physics, information is local. The information about an object is stored in that object or its immediate vicinity. A book contains information in the arrangement of ink on its pages. A computer stores information in magnetic domains on a hard drive or charge states in memory chips. This information is physically located somewhere specific. But in quantum mechanics, information can be genuinely non-local. The information about an entangled pair doesn't reside in either particle individually. It exists in the relationship between them, in the pattern of correlations that link them together. Each particle, considered alone, is in a mixed state, a statistical mixture that contains no definite information. The information emerges only when you consider both particles together, when you look at how measurements on one relate to measurements on the other. This has profound implications. It means quantum systems can store and process information in ways that have no classical analog. It's part of what makes quantum computers potentially so powerful. They can manipulate information encoded in entangled states, information that's distributed across many particles in intricate patterns. It also means that destroying a quantum system doesn't necessarily destroy all the information it contained, if that information was entangled with another system that survives. Entanglement can involve more than two particles. You can have three particles entangled together, or four, or in principle any number. As the number of entangled particles grows, the quantum system becomes exponentially more complex. With two particles, you need to specify correlations between two systems. With three, you need three-way correlations. With many particles, the correlations become vastly intricate, impossible to fully describe or visualize. This is part of what makes quantum computers so powerful. They can manipulate many entangled particles simultaneously, exploring vast spaces of possibility in parallel. It's also what makes quantum systems so difficult to simulate on classical computers. The information needed to describe an entangled state of many particles grows exponentially with the number of particles. A system of just 300 entangled particles requires more numbers to fully describe than there are atoms in the observable universe. Classical computers can't handle this complexity, but quantum computers can, because they're made of quantum systems that naturally live in these vast state spaces. Entanglement is fragile. Interactions with the environment, things like stray photons of thermal radiation, vibrations, electromagnetic noise, can break the entanglement, a process called decoherence. The quantum system becomes entangled with its environment, and the delicate correlations between the particles of interest get washed out, spread across countless environmental degrees of freedom that we can't track or control. This is why quantum computers need to be isolated so carefully, kept at temperatures near absolute zero in vacuum chambers, shielded from any disturbance. Maintaining entanglement long enough to perform useful computations is one of the great challenges of quantum technology. It's important to understand what entanglement is not. It's not some invisible thread connecting particles. No physical stuff stretching between entangled particles that lets them communicate. There's no medium carrying signals back and forth. Rather, entanglement is a property of how the particles were prepared, a correlation built into their shared quantum state when they interacted. Once entangled, they remain correlated no matter how far apart they drift, until something disrupts that correlation through decoherence or through measurement. Entanglement also doesn't mean that particles are always correlated in simple ways. The nature of the correlation depends on how the entangled state was created and what measurements you choose to make. Different types of measurements can reveal different patterns of correlation. You might measure polarization, or momentum, or energy, or spin along various axes. Each type of measurement probes a different aspect of the entangled state. This is part of what makes entanglement so rich and useful. By choosing different measurements, you can extract different kinds of information from the entangled state. Some physicists, including those working on interpretations of quantum mechanics, argue that entanglement suggests the universe is fundamentally holistic rather than reductionist. We can't understand the whole by just understanding the parts, because the parts aren't independent entities. They're aspects of interconnected quantum systems. In this view, separation and individuality, the way we carve the world up into distinct objects, is an illusion that emerges only at macroscopic scales, when quantum effects become invisible through decoherence. At the deepest level, everything is entangled with everything else, and the appearance of separate, independent objects is just an approximation that works well for everyday purposes but breaks down when you look closely enough. Bell's theorem, the revolution in our understanding. For decades after Einstein proposed the EPR paradox, the question seemed philosophical rather than scientific. How could you possibly test whether quantum mechanics is complete or whether there are hidden variables? The mathematics of quantum mechanics worked perfectly for calculating probabilities, and that was enough for practical purposes. But in 1964, a soft-spoken Irish physicist named John Stuart Bell changed everything. He proved that the debate between Einstein and Bohr wasn't just philosophical. It could be settled with experiments. Bell was working at CERN, the European Particle Physics Laboratory, but he thought deeply about the foundations of quantum mechanics in his spare time. He wanted to know whether Einstein might be right, whether there could be hidden variables determining the outcomes that quantum mechanics describes as random. Bell devised a brilliant argument, now known as Bell's theorem, which showed that local hidden variable theories make predictions that differ from quantum mechanics in specific, measurable ways. The core of Bell's argument involves comparing correlations. Imagine you have a pair of entangled particles flying apart in opposite directions. You and a friend each have a detector. You can set your detector to measure the particles' property along different axes, say vertical versus horizontal, or diagonal one way versus diagonal the other way. Your friend can independently choose which axis to measure along. You perform many trials, randomly choosing your measurement axis, and then compare results. Bell showed that if local hidden variables exist, if each particle carries information determining how it will respond to any possible measurement, then the correlations you observe must satisfy certain inequalities, now called Bell inequalities. These inequalities set limits on how strongly correlated the results can be. Quantum mechanics, however, predicts violations of these inequalities. In certain configurations, quantum correlations are stronger than any local hidden variable theory can produce. This was a stunning result. Bell had shown that quantum mechanics and local realism make different predictions. Moreover, these predictions could, in principle, be tested. If experiments showed violations of Bell's inequalities, it would prove that nature is non-local, that distant measurements really are coordinated in ways that can't be explained by local hidden information. Einstein's hope that quantum mechanics could be supplemented with hidden variables would be dashed. The first experiments to test Bell's inequalities were performed in the 1970s and early 1980s, most famously by Alain Aspect and his colleagues in France. These experiments used entangled photons created through atomic cascades. The photons flew to detectors placed several meters apart, where their polarizations were measured along randomly chosen axes. The setup had to be very carefully designed to ensure that the choice of measurement on one side couldn't influence the other side through any normal means. The results were clear and have been confirmed in countless experiments since. Bell's inequalities are violated. The correlations observed in entangled systems are stronger than local hidden variables can explain. Nature is non-local. Einstein was wrong. There are no hidden variables determining the measurement results in advance. The randomness of quantum mechanics is fundamental, not just a reflection of our ignorance. And the spooky action at a distance, the instantaneous correlation between distant measurements, is real. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their pioneering experiments with entangled photons. Clauser performed some of the earliest tests of Bell's inequalities in the 1970s. Aspect refined the experiments in the 1980s, closing loopholes and making the results more definitive. Zeilinger pushed the boundaries further, demonstrating entanglement over longer distances and developing techniques that led to applications in quantum information. These experiments fundamentally changed our understanding of reality. They showed that the world is not made of separate, independent objects with their own private properties. At the quantum level, systems are interconnected in ways that transcend space. The measurement you make here can be correlated with a measurement over there in a manner stronger than classical physics allows. This doesn't mean information travels faster than light, but it does mean that the classical concept of locality, the idea that influences propagate at finite speeds, doesn't hold in quantum mechanics. Interestingly, Bell himself was somewhat ambivalent about his discovery. He had hoped to find that Einstein was right, that there might be hidden variables restoring a sensible, realistic view of the world. Instead, his theorem showed that if you want to keep realism, you have to abandon locality. Or, if you want to keep locality, you have to abandon realism. Either way, something deeply counterintuitive about quantum mechanics is correct. Some interpretations of quantum mechanics, like the many worlds interpretation, try to preserve a kind of realism by proposing that all possible measurement outcomes actually occur in different branches of reality. Others, like the de Broglie-Bohm-Pilot wave theory, introduce nonlocal hidden variables that guide particles along definite paths. These approaches avoid some aspects of the Copenhagen interpretation's weirdness, but introduce their own conceptual challenges. The violations of Bell's inequalities don't tell us which interpretation is correct, but they do rule out entire classes of theories. The philosophical implications are profound. We live in a universe where spatially separated events can be correlated in ways that seem to defy our intuitive understanding of cause and effect. The experiments proving Bell's theorem violations are among the most important in the history of physics, right alongside Galileo's experiments with falling bodies and the detection of gravitational waves. They force us to rethink what we mean by reality itself, seeing the invisible, visualizing entangled states. For most of quantum mechanics' history, entanglement was an invisible phenomenon. You could measure its effects, observe the correlations it produces, but you couldn't actually see the entangled state itself. It existed as a mathematical abstraction, a wave function describing two particles together. But in recent years, scientists have developed remarkable techniques that come close to visualizing entanglement, making the invisible visible. In 2023, a team of researchers led by scientists at the University of Ottawa published images that showed, for the first time, the wave function of two entangled photons. Using a technique called quantum holography, they captured the full quantum state of the entangled pair. Not just the correlation between measurements, but the underlying wave function itself. The resulting image was beautiful and eerie, showing an intricate pattern of light and dark that resembled a yin-yang symbol, the ancient representation of complementary forces. The technique works by interfering the entangled photons with reference beams, similar to how holography captures three-dimensional images of objects. When waves overlap, they create interference patterns, regions where they reinforce each other and regions where they cancel out. By carefully measuring these patterns, the researchers could reconstruct the complex valued wave function, both its amplitude and its phase. This wave function contains all the information about the entangled state, everything quantum mechanics can tell you about the two photons. Looking at these images, you can almost feel the strangeness of quantum mechanics. The pattern doesn't look like two separate things. It looks like a single, unified structure. Waves of possibility flowing through space, binding the photons together in an embrace that persists across distance. The yin-yang resemblance is not just aesthetic. It reflects the complementary nature of the entangled photons, how the state of one is defined in relation to the other. This visualization breakthrough is more than just pretty pictures. It has practical applications for quantum technology. To build quantum computers and quantum communication systems, you need to create specific entangled states and verify that you have created them correctly. Measuring the wave function allows you to check your work to ensure that the entanglement has the properties you need. It also helps researchers understand how entanglement behaves in different situations, how it evolves, and how it can be manipulated. Other techniques have allowed scientists to visualize entanglement in different ways. Some experiments use weak measurements, a method that gently probes a quantum system without fully collapsing it, to track how entanglement builds up as particles interact. Others use tomography, taking many measurements from different angles to reconstruct the quantum state, similar to how a CT scan builds a three-dimensional image of the body from two-dimensional X-rays. These advances bring quantum mechanics out of the realm of pure abstraction. When you can see the wave function, when you can watch entanglement form and evolve, it becomes more tangible, more real. It's no longer just equations on a blackboard. It's patterns of light and shadow, structures you can point to and say, "There, that's what quantum mechanics looks like." The images also serve an educational purpose. For students and the public, entanglement can seem impossibly abstract, a paradox described in words that never quite make sense. But when you show someone the yin-yang pattern of an entangled state, when you explain that this is the actual shape of the quantum wave function, understanding deepens. The mystery doesn't go away. Quantum mechanics remains counterintuitive, but it becomes a concrete mystery rather than an abstract one. As techniques improve, scientists hope to visualize even more complex, entangled states, systems with 3, 4, or many particles. These many particle entangled states are the workhorses of quantum computing, and being able to see their structure could lead to new insights into how to create and control them. It might also reveal new patterns, new types of entanglement that could be useful for applications we haven't yet imagined. The quantum computer revolution. Quantum entanglement isn't just a curiosity, a strange feature of nature to marvel at. It's the foundation of a technological revolution currently underway. Quantum computers, which harness entanglement to perform calculations impossible for classical computers, are moving from laboratory demonstrations to practical devices. Understanding how entanglement powers these machines reveals why they're so fundamentally different from the computers we use every day. A classical computer processes information as bits, each either 0 or 1. Everything the computer does, from displaying this text to running complex simulations, comes down to manipulating these bits through logical operations. A quantum computer, by contrast, uses quantum bits, or qubits, which can exist in superposition of 0 and 1 simultaneously. This might seem like a small change, but combined with entanglement, it creates exponentially greater computational power. Here's why entanglement matters. If you have 3 classical bits, they can be in one of 8 possible states at any moment: 0, 001, 010, and so on. But they're always in exactly one of those states. 3 qubits, however, can be in a superposition of all 8 states at once. More importantly, if the qubits are entangled, they don't just represent 8 independent possibilities. They represent a single unified quantum state where information is distributed across all 3 qubits in intricate ways. When you perform operations on entangled qubits, you're manipulating all those possibilities simultaneously. It's as if the quantum computer is exploring many different computational paths at the same time, a phenomenon called quantum parallelism. This doesn't mean a quantum computer can solve any problem faster than a classical computer. In fact, for many everyday tasks, classical computers are perfectly fine. But for certain types of problems, particularly those involving searching large spaces or simulating quantum systems themselves, quantum computers can achieve speedups that grow exponentially with the number of qubits. One famous example is Shor's algorithm, discovered in 1994 by mathematician Peter Shor. This algorithm can factor large numbers exponentially faster than the best-known classical algorithms. Factoring is the basis of much modern cryptography. The RSA encryption that protects your credit card numbers and emails relies on the fact that factoring large numbers is very hard. A quantum computer running Shor's algorithm could break this encryption, which is why there's now a race to develop quantum-resistant cryptographic methods. Another important algorithm is Grover's algorithm, which can search an unsorted database quadratically faster than classical methods. If you need to find a specific item among a million possibilities, a classical computer might need to check about 500,000 on average. Grover's algorithm can find it in roughly 1,000 steps. This speedup applies to many optimization problems, where you're searching for the best solution among countless options. Creating and maintaining entanglement between qubits is extraordinarily difficult. Qubits are typically implemented using physical systems like superconducting circuits, trapped ions, or photons. These systems are incredibly delicate. Any interaction with the environment, even a stray photon of thermal radiation, can cause decoherence, destroying the entanglement. This is why quantum computers need to be kept at temperatures near absolute zero, colder than outer space, and shielded from electromagnetic interference. Different technologies for building qubits have different advantages. Superconducting qubits, used by companies like Google and IBM, can be manufactured using techniques borrowed from semiconductor industry and are relatively easy to integrate into complex circuits. But they require extreme cooling and have short coherence times, meaning entanglement only lasts for microseconds. Trapped ion qubits, used by companies like IonQ, have much longer coherence times and high-fidelity operations, but they're harder to scale to large numbers. Photonic qubits, qubits encoded in particles of light, have the advantage that photons don't easily interact with their environment, so they can maintain entanglement even at room temperature. They're also natural carriers of quantum information over long distances, making them ideal for quantum communication. But manipulating photons and getting them to interact with each other is technically challenging. Researchers are exploring many other physical systems too, from neutral atoms to diamond defects to topological qubits. A major focus of quantum computing research is error correction, because qubits are so fragile and operations on them imperfect, errors accumulate quickly. Quantum error correction schemes use entanglement in clever ways to detect and fix errors without measuring the qubits directly, which would destroy their superposition. By entangling many physical qubits together, you can create a single logical qubit that's protected against errors. But this requires tremendous overhead. You might need hundreds or thousands of physical qubits to make one reliable logical qubit. Companies and research institutions around the world are racing to build practical quantum computers. Google announced a milestone called quantum supremacy in 2019, performing a calculation on their 53-qubit processor that would take a classical supercomputer thousands of years. IBM, Microsoft, Amazon, and numerous startups are developing their own quantum hardware and software. China has invested heavily in quantum technology, launching the world's first quantum communication satellite and building quantum computers that have achieved their own supremacy milestones. The applications being explored go far beyond cryptography. Quantum computers could revolutionize drug discovery by simulating how molecules interact, helping design new medicines. They could optimize logistics, finding efficient routes for deliveries or schedules for airlines. They could accelerate machine learning, finding patterns in data more quickly. They could help design new materials with specific properties, like better batteries or more efficient solar cells. But we're still in the early days. Current quantum computers are what's called noisy intermediate-scale quantum devices, or NISQ. They have tens or hundreds of qubits, enough to do interesting experiments but not enough to run the full quantum algorithms that promise revolutionary speedups. Those algorithms require thousands or millions of qubits with error correction, which might still be years or decades away. The field is advancing rapidly, though, with new techniques for creating, controlling, and connecting qubits announced regularly. Applications beyond computing, the quantum technology frontier. While quantum computers capture the most attention, entanglement enables a whole ecosystem of quantum technologies. These applications, some already in practical use and others still being developed, demonstrate that entanglement is more than a scientific curiosity. It's a resource, as fundamental to future technology as electricity or semiconductors. Quantum cryptography, particularly quantum key distribution, is perhaps the most mature quantum technology. It uses entangled photons to create encryption keys that are provably secure, guaranteed by the laws of physics rather than the difficulty of mathematical problems. Here's how it works. Two parties, conventionally named Alice and Bob, share pairs of entangled photons. They each measure their photons along randomly chosen axes, and then communicate classically to compare notes on which axes they chose. Because the photons are entangled, When Alice and Bob happen to choose the same measurement axis, their results are perfectly correlated. They can use these correlated results to build a secret key. Here's the clever part. If an eavesdropper, Eve, tries to intercept the photons to learn the key, she necessarily disturbs the quantum state. This disturbance is detectable. The correlations between Alice and Bob's measurements will be weakened. They'll know someone is listening and can abort the key exchange. This security is unconditional. It doesn't depend on assumptions about the computational power of potential attackers. Even a quantum computer can't break quantum cryptography without being detected. Several companies now sell quantum key distribution systems, and governments are deploying quantum-secure communication networks. China has built a quantum communication network spanning thousands of kilometers, using both fiber optic cables and satellite links. The European Union and other regions are developing similar infrastructure. Quantum teleportation is another application, though it's not what science fiction fans might hope. You can't teleport objects or people. What you can teleport is quantum states. Suppose Alice has a qubit in an unknown state and wants to send that state to Bob, who's far away. Using entanglement, she can achieve this without physically transmitting the qubit itself. Alice and Bob share an entangled pair of qubits in advance. Alice then performs a joint measurement on her qubit and her half of the entangled pair. This measurement destroys the original state but provides information she sends to Bob classically. Bob uses this information to perform an operation on his half of the entangled pair, which transforms it into a copy of the original qubit. The state has been teleported, disappearing from Alice's location and reappearing at Bob's. This works even though Alice never knew what the state was. Quantum mechanics prevents her from determining it exactly. Teleportation has been demonstrated over hundreds of kilometers and is a key component in the proposals for quantum internet, a network where quantum information can be distributed between quantum computers and other quantum devices. Quantum sensors exploit entanglement to make measurements more precise than classical sensors can achieve. The principle is that entangled states can be more sensitive to small changes in the environment. For example, atomic clocks, already the most precise timekeeping devices, can be improved by using entangled atoms. Entanglement allows the atoms to collectively sense time's passage, reducing random fluctuations and improving accuracy. These super-precise clocks have applications in GPS navigation, financial trading, and testing fundamental physics. Gravitational wave detectors like LIGO might be enhanced with entanglement. By entangling the photons in the laser beams that measure the detector's arms, researchers could reduce quantum noise and detect even weaker ripples in space-time. This could open windows on more distant or subtle astrophysical events. Medical imaging might benefit too, with entangled photons allowing lower radiation doses or higher resolution images. Quantum simulation is using one quantum system to model another. Some materials and chemical reactions involve quantum effects that are impossible to simulate on classical computers. The number of variables explodes exponentially. But a quantum computer, itself a quantum system, can naturally represent these quantum states. This could lead to breakthroughs in understanding high-temperature superconductors, designing new catalysts for chemical reactions, or predicting how proteins fold. There are even speculative applications in biology. Some researchers believe quantum effects, possibly including entanglement, play a role in processes like photosynthesis and bird navigation. If true, understanding and harnessing these effects could lead to more efficient solar cells or novel sensing technologies. The field of quantum biology is controversial, with debates over whether quantum coherence can persist long enough in warm, wet biological systems to be functionally important. But experiments continue to explore the boundaries. Looking further ahead, a quantum internet would connect quantum computers and quantum sensors, allowing them to share entanglement and quantum information. This could enable distributed quantum computing, where multiple quantum processors work on a problem together, or secure multi-party computations where participants learn a result without revealing their inputs to each other. Proposals exist for quantum versions of blockchain technology, quantum machine learning, and quantum artificial intelligence. The challenges are immense. Distributing entanglement over long distances requires overcoming photon loss in fibers and maintaining coherence through atmospheric turbulence for satellite links. Interfacing different quantum systems, say, connecting a superconducting qubit to a photon for communication, requires exquisite control. Scaling up from laboratory demonstrations to practical networks demands engineering advances in miniaturization, automation, and reliability. But progress is steady. Every few years brings demonstrations that once seemed impossible. Entanglement has been distributed between satellites and ground stations. Quantum repeaters, devices that extend entanglement over longer distances by swapping it between successive segments, are being developed. Companies are offering cloud access to quantum computers, and researchers are writing software to run on them. The quantum technology era is beginning. Entanglement in nature. Does the universe compute quantum mechanically? One of the most fascinating questions about entanglement is whether it plays a role not just in engineered systems, but in nature itself. After all, quantum mechanics governs the atomic and molecular world, and entanglement is a fundamental feature of quantum mechanics. Could nature be using entanglement in ways we're only beginning to discover? Photosynthesis, the process by which plants convert light into chemical energy, has revealed surprising quantum features. When a photon strikes a chlorophyll molecule, it excites an electron. This excitation must be transferred to a reaction center where it can do useful work. But the path isn't straightforward. There are multiple possible routes through a complex network of molecules. Experiments have shown that the energy transfer happens with remarkable efficiency, far higher than you'd expect if the excitation simply randomly walked through the network. Researchers have found evidence of quantum coherence in photosynthesis, suggesting that the excitation explores multiple paths simultaneously as a quantum superposition. This allows it to find the most efficient route almost instantaneously. Some models propose that entanglement between different molecular sites might play a role, creating a quantum search algorithm that nature evolved long before humans invented quantum computers. The evidence is still debated, and it's unclear how quantum coherence could survive in the warm and noisy environment of a living cell, but the possibility is tantalizing. Another intriguing case involves bird navigation. Many bird species can sense the Earth's magnetic field and use it for orientation during migration. The leading theory for how they do this involves radical pair mechanism, a quantum effect where a chemical reaction's outcome depends on the spins of two electrons. These spins can be entangled, and an external magnetic field, even one as weak as Earth's, can influence the reaction by affecting the entangled state. Specialized proteins in birds' eyes might act as quantum sensors for magnetism. When light strikes these proteins, it creates radical pairs with entangled electrons. The magnetic field influences how these pairs recombine, changing the chemical products in ways that could be detected by the bird's nervous system. Experiments have shown that disrupting this quantum process with artificial magnetic fields can disorient birds, supporting the theory. If true, it means birds are carrying quantum compasses in their heads, using entanglement to navigate across continents. The question of whether quantum effects, including entanglement, play roles in consciousness is highly speculative and controversial. Some researchers, most famously physicist Roger Penrose and anesthesiologist Stuart Hameroff, have proposed that quantum processes in structures called microtubules inside neurons might be involved in how the brain generates conscious experience. This theory, called orchestrated objective reduction, or OR, suggests that entanglement between quantum states in microtubules could give rise to the unified nature of consciousness. Most neuroscientists are skeptical. The brain is warm and wet, conditions that should destroy quantum coherence almost instantly. Critics argue that consciousness can be explained by classical neural activity without invoking quantum mechanics. Penrose and Hameroff counter that biological systems might have evolved ways to protect quantum states, similar to how quantum computers are shielded from decoherence. Experiments to test the theory are difficult, and the debate continues. Even if entanglement doesn't play a functional role in biology, it's certainly present at the atomic and molecular level in living organisms. Every chemical bond has quantum character, and electrons in molecules exist in entangled states. The question is whether these quantum effects matter for biological functions, or whether they're just microscopic details that average out to classical behavior at larger scales. Looking at the cosmos, entanglement might be woven into the fabric of space-time itself. Some theories in quantum gravity propose that the geometry of space and time emerges from entanglement in a quantum system. In this view, what we perceive as the smooth curvature of space-time around a massive object is actually a pattern of quantum entanglement between microscopic degrees of freedom. The connections between different regions of space, the fact that distant locations are part of the same universe, might be explained by the entanglement of their underlying quantum states. This idea connects to a concept called the holographic principle, which suggests that the information in a volume of space is encoded on its boundary. Entanglement provides a way to understand how information on the boundary translates to the interior structure. Researchers studying black holes have found that entanglement entropy, measure of how entangled a quantum system is, behaves in ways that mirror the entropy of black holes, deepening the connection between quantum information and gravity. These ideas are at the cutting edge of theoretical physics, and many details remain to be worked out. But they suggest that entanglement isn't just a feature that appears in certain quantum systems. It might be a fundamental organizational principle of the universe, connecting matter and energy, space and time, in a cosmic web of correlation. The future, quantum internet and beyond. As we look to the future, entanglement is poised to become the backbone of new global infrastructure. The vision of a quantum internet, where quantum computers, sensors, and other devices are linked by shared entanglement, is moving from science fiction toward science fact. This network would enable capabilities impossible with classical communication, from unconditionally secure messaging to distributed quantum computing to new forms of sensing and metrology. Building a quantum internet requires solving several technical challenges. First, you need sources that can produce entangled photons on demand with high fidelity. Researchers have developed quantum dots, semiconductor nanostructures that emit single photons, and parametric down-conversion crystals that reliably create entangled pairs. These sources are improving in efficiency and brightness, though there's still work to do before they match the performance needed for a large-scale network. Second, you need quantum memories that can store entangled states reliably. Photons are great for transmitting quantum information. They travel at light speed and don't easily interact with the environment. But they're hard to store. You can't slow light down and hold it in place very easily. Quantum memories, typically using atoms or rare earth ions in crystals, can absorb a photon and store its quantum state, then re-emit it on demand. Good quantum memories need to have high efficiency, long storage times, and the ability to interface with communication photons. Progress is being made, but it's one of the harder problems. Third, for long distances, you need quantum repeaters. When you send photons through optical fiber, they get absorbed or scattered, and eventually the signal is lost. In classical communication, you just amplify the signal periodically. But you can't amplify a quantum state without disturbing it. Measurement and copying are forbidden by the no-cloning theorem. Instead, quantum repeaters work by breaking the link into short segments, creating entanglement across each segment, and then connecting these segments through entanglement swapping. This extends the range without requiring the original photons to travel the full distance. China has taken a leading role in developing quantum communication infrastructure. Their quantum satellite, Mikius, launched in 2016, has demonstrated entanglement distribution between ground stations separated by over 1,000 kilometers. The satellite generates entangled photon pairs and sends one to each station. Because the photons travel through the vacuum of space most of the way, losses are much lower than in fiber optics. China has also built terrestrial quantum networks connecting Beijing, Shanghai, and other cities, using quantum key distribution for secure government and financial communications. Europe and the United States are developing their own quantum networks. The U.S. Department of Energy has outlined a blueprint for a national quantum internet, with prototype networks already operating between research laboratories. The European Quantum Communication Infrastructure Initiative aims to connect quantum networks across the continent. Private companies are getting involved too, offering quantum communication services and developing the necessary hardware. The applications of a quantum internet extend beyond secure communication. Distributed quantum computing would allow multiple quantum processors to work together on problems too large for any single machine. Imagine a complex simulation split across quantum computers in different cities, with entanglement linking them so they function as one unified system. Or consider quantum sensor networks, where entanglement between sensors improves their collective precision, enabling applications like more accurate GPS, better gravitational wave detection, or even searching for dark matter. Fundamental physics could benefit enormously. Quantum internet could connect atomic clocks separated by vast distances, making them more precise through entanglement. This could enable tests of general relativity with unprecedented accuracy, or searches for variations in fundamental constants. Telescopes separated by continental or even interplanetary distances could be linked quantum mechanically, achieving resolutions far beyond what single instruments can manage. There are also fascinating proposals for quantum blockchain and quantum money. Classical cryptocurrencies rely on computational difficulty to ensure security, but quantum computers threaten to break these systems. Quantum blockchain schemes use entanglement and other quantum effects to create distributed ledgers that are information theoretically secure. Quantum money would be physical tokens, perhaps photons or quantum states in atoms, whose states cannot be cloned, making counterfeiting impossible. Looking even further ahead, some researchers envision quantum networks extending into space, linking Earth-based quantum devices with those on satellites, space stations, or even other planets. Entanglement could enable secure communication with interplanetary probes, or quantum sensing of gravitational fields across the solar system. The distances involved present extreme challenges, but the fundamental physics doesn't forbid it. As quantum technologies mature, questions about standards and interoperability will become important. Just as the Internet relies on protocols like TCP+IP that allow different systems to communicate, a quantum Internet will need its own protocols. How do you route quantum information? How do you ensure different quantum hardware platforms can exchange entangled states? Working groups are beginning to address these questions, drawing on lessons from classical networking. There are also societal implications to consider. Quantum cryptography could make surveillance much harder, empowering privacy. Or it could be controlled by governments and corporations, creating new forms of information control. Quantum computers might break current encryption, requiring a transition to quantum-resistant cryptography to protect existing data. The timeline for these transitions is uncertain, making planning difficult. Philosophically, a quantum internet would make entanglement part of everyday infrastructure, something ordinary rather than exotic. Just as most people use GPS without thinking about the relativistic corrections that make it work, future generations might use quantum communication without marveling at the entanglement that enables it. The strangeness of quantum mechanics would become mundane, domesticated, a tool rather than a mystery. Yet the mystery wouldn't truly disappear. Each time entanglement is created and distributed, each time distant particles respond in coordinated ways that classical physics can't explain, the deep weirdness of quantum mechanics would still be there, hidden beneath the user interface. We'd be building a civilization on foundations that, when you look closely, don't make intuitive sense, that challenge our most basic notions about the nature of reality. The philosophical depths, what entanglement teaches us. Beyond its practical applications and scientific significance, quantum entanglement raises profound philosophical questions about the nature of reality. These questions have occupied philosophers and physicists for nearly a century, and answering them, or even clarifying them, remains an active area of inquiry. Entanglement challenges several assumptions we make about the world, and examining these challenges can deepen our understanding of both quantum mechanics and our own place in the cosmos. The first and perhaps deepest question concerns the nature of reality itself. Classical physics assumed a world of objects with definite properties existing independently of observation. A rock has a certain mass and position whether or not anyone is looking at it. But quantum mechanics, particularly in the Copenhagen interpretation, suggests that properties don't exist in a definite state until measured. The wave function describes possibilities, and measurement collapses those possibilities into actualities. Entanglement intensifies this puzzle. When two particles are entangled, neither has definite properties on its own. They're described by a joint wave function, and only when you measure one does it, and simultaneously its partner collapse into definite states. This suggests that reality is fundamentally relational. Properties aren't intrinsic to objects, but arise from interactions and measurements. The particle doesn't have a spin in isolation. It has a spin relative to a measurement apparatus and relative to its entangled partner. Some interpretations try to restore a more classical picture. The de Broglie-Bohm pilot wave theory proposes that particles do have definite positions at all times, guided by a wave that evolves according to quantum mechanics. But to account for entanglement and Bell's theorem violations, this wave must be nonlocal, instantly influencing particles across any distance. So you regain reality, but at the cost of accepting non-locality explicitly. The many worlds interpretation takes a different approach. It says that all possible measurement outcomes actually occur, each in a different branch of reality. When you measure an entangled particle and find it spinning up, the universe splits. There's a version of you seeing spin up and another version seeing spin down. Entanglement is explained by correlations between branches. This interpretation avoids wave function collapse and preserves a kind of determinism, but at the cost of an infinity of unseen parallel worlds. Other interpretations, like cubism or relational quantum mechanics, emphasize the role of the observer and treat quantum states as descriptions of knowledge or perspectives rather than objective features of reality. Each of these approaches handles entanglement differently, and none has emerged as definitively correct. The choice between them often comes down to which aspects of common sense you're willing to give up. Another philosophical issue involves causality. Entanglement seems to involve some form of action at a distance, but it doesn't fit neatly into our usual categories of cause and effect. When you measure one particle, does this cause the other to take a definite state? If so, the causation is instantaneous, faster than light, which seems to violate relativity. But if you can't use this connection to send information, is it really causation in the usual sense? Some philosophers argue that entanglement shows causation isn't fundamental. What's fundamental are correlations, patterns in nature that don't necessarily have a causal explanation. The entangled particles are correlated because of how they were prepared, not because measuring one sends a signal to the other. This requires rethinking our intuitions about how events are related, accepting that correlation can exist without underlying causation. Entanglement also raises questions about individuality and identity. If two particles are entangled, are they really two separate things? Their properties can't be described independently. In a sense, they're more like two aspects of a single entity spread across space. This holistic view challenges the reductionist approach that has dominated science for centuries. Reductionism says you can understand the whole by understanding the parts. But with entanglement, there aren't truly independent parts. The whole is primary. This has echoes in Eastern philosophies which often emphasize interconnectedness and the illusory nature of separate identity. Some physicists and philosophers have drawn parallels between quantum mechanics and Buddhist or Taoist concepts. While these parallels can be overstated, there's something genuinely interesting in the way quantum mechanics forces us toward a more holistic, relational view of reality, resembling ideas that existed in non-Western traditions long before quantum theory. There is also the question of determinism. Classical physics was deterministic. If you know the exact state of a system, you can predict its future with certainty. Quantum mechanics is probabilistic. You can predict the likelihood of different outcomes, but not which will occur in any single instance. Einstein found this troubling, leading to his famous remark that God doesn't play dice. But if the randomness is fundamental, if the universe is intrinsically probabilistic, what does this mean for notions like free will, or the predictability and knowability of nature? Some argue that quantum randomness leaves room for free will, that human choices aren't predetermined because quantum events in the brain aren't predetermined. Others counter that randomness isn't the same as freedom, that truly random events are just as uncontrolled as deterministic ones. The debate touches on deep questions about agency, responsibility, and the nature of the self. Finally, entanglement might teach us something about the unity of the universe. In the Big Bang, all the matter and energy in the universe was concentrated in an incredibly small, hot, dense state. Everything was interacting with everything else. In that early fireball, essentially the entire universe was entangled. As the universe expanded and cooled, much of this entanglement would have been scrambled by decoherence, washed out into the environment, but traces might remain. Some physicists speculate that long-range entanglement might still thread through the cosmos, linking distant galaxies, or even providing a foundation for space-time itself. If everything ultimately came from the same source, then, in some sense, everything remains connected. Entanglement could be the universe's way of remembering that it was once a unified whole. This is poetic, perhaps, but it's grounded in the real physics of how quantum systems evolve. Closing reflections, the wonder remains. As we've wandered through the landscape of quantum entanglement, from Einstein's initial resistance to the latest visualizations and technologies, one truth stands clear. The universe is stranger, more interconnected, and more wonderful than our everyday experiences prepare us to expect. Entanglement reveals that reality, at its deepest level, doesn't respect the boundaries we draw. Particles separated by cosmic distances remain joined in an invisible embrace. The act of observation here determines what happens there. Information about the whole doesn't reduce to information about the parts. This strangeness isn't a flaw in quantum mechanics, a sign that the theory is incomplete or incorrect. It's a feature of nature itself, confirmed by decades of experiments, recognized by Nobel Prizes, and now being harnessed to build the quantum technologies that will shape our future. We're learning to work with entanglement, to create it on demand, to preserve it long enough to perform computations or transmit information. We're building quantum computers that manipulate entangled states to explore vast spaces of possibility. We're developing quantum communication networks that use entanglement to guarantee security. Yet, even as we put entanglement to work, the sense of mystery persists. How can particles be correlated without any signal passing between them? What does it mean for properties to not exist until measured? Why does the universe operate according to these bizarre quantum rules? These questions remain alive, not as obstacles to progress, but as invitations to deeper understanding. They remind us that science isn't just about mastering nature, but about marveling at it. Think about what entanglement reveals about the nature of connection itself. In our daily lives, we understand connection through proximity and through communication. We're connected to people nearby, to those we talk with, to communities we're part of through shared experiences and ongoing contact. Distance and silence create separation. But quantum entanglement presents a form of connection that transcends space and doesn't require any ongoing communication. Particles that interacted once, perhaps billions of years ago in the early universe, might still carry traces of that interaction as subtle correlations that persist across space and time. This suggests that the universe has a kind of memory written into its quantum structure. Events that happened long ago still matter, still shape what's possible now. The entanglement created in the Big Bang, when everything was crushed together in a point smaller than an atom, might still linger in the cosmic microwave background radiation that fills the sky. Studying these correlations could tell us about the earliest moments of the universe, about conditions when space and time themselves were just emerging from the quantum foam. For you, resting in the darkness, quantum entanglement might seem distant from daily concerns. But in a very real way, you're already entangled with the universe. The atoms in your body were forged in stars, scattered by supernovas, and gathered into planets. The particles that make you up have histories stretching back to the Big Bang. They've interacted with countless others, forming and breaking entanglements, leaving traces of connection across space and time. You are not separate from the cosmos. You're a pattern in the quantum field, a temporary arrangement of matter and energy that the universe has taken, connected to everything that was and is and will be. The carbon atoms in your DNA, the oxygen you breathe, the calcium in your bones, all were created in stellar furnaces, or in the violent explosions that ended massive stars. These atoms once were parts of other structures, other worlds, other beings perhaps. Through their quantum properties, through the entanglements they have participated in over cosmic time, they carry an invisible history that connects you to the furthest reaches of space and the deepest past of time. This perspective can be comforting or unsettling, depending on your mood. It dissolves the boundaries that make us feel isolated, showing that we are part of something vast and interconnected. But it also challenges our sense of individuality, suggesting that the separate self is, at some level, an illusion. Both views have truth in them. We are individuals with unique experiences and perspectives, and we are also nodes in a cosmic network, entangled with the whole. Modern physics increasingly suggests that these two aspects of reality, the individual and the universal, aren't contradictory but complementary. Yes, you have a unique perspective, a particular arrangement of matter that thinks and feels and experiences the world in ways no one else ever has or will. And yes, you're made of the same fundamental stuff as everything else, obeying the same quantum rules, participating in the same interconnected quantum field that underlies all of reality. Both truths can coexist. Quantum entanglement might even offer insights into questions that seem far removed from physics. Some philosophers and cognitive scientists wonder whether consciousness itself might be understood through quantum mechanics. Could the unity of conscious experience, the way disparate sensations and thoughts come together into a single, integrated awareness, have something to do with quantum coherence or entanglement in the brain? This remains highly speculative, and most neuroscientists are skeptical. But the questions persist because consciousness, like quantum mechanics, seems to involve properties that resist reduction to simple parts. If you've enjoyed this journey through the quantum realm, I hope you'll consider liking this video and subscribing to Sleepy Science Society. These explorations take time to research and create, and your support makes them possible. It helps the channel grow, bringing more people into this space where we can contemplate the deep mysteries of nature together. Share your thoughts in the comments. Tell me what fascinates you about quantum entanglement, or what questions it raises for you. Science is a conversation, and I'd love to hear your voice in it. The community that gathers around science, around these questions about the deep nature of reality, is itself a kind of network. Each person brings their own perspective, their own questions, their own insights. Together, we explore further than any individual could alone. This collaborative aspect of science mirrors, in a way, the collaborative aspect of quantum mechanics itself, where information is shared across systems, where the whole emerges from intricate correlations between parts. For now, though, just rest. Let the ideas we've explored tonight settle gently into your mind. You don't need to understand everything. Quantum mechanics resists complete understanding. Even the physicists who work with it every day are comfortable with the mystery. Richard Feynman, one of the great quantum physicists of the 20th century, famously said, "I think I can safely say that nobody understands quantum mechanics." He didn't mean that we can't use it or predict with it. We can do both with extraordinary precision. He meant that the conceptual foundations, the interpretation of what's really happening, remains elusive. What matters is that you've touched something profound. Something that reveals the universe as more subtle, more interconnected, more beautiful than surface appearances suggest. You've glimpsed a realm where the rules shift, where possibilities dance in superposition, where distant particles share a quantum embrace across the void. This glimpse, even if incomplete, even if fragmentary, enriches your understanding of the world. It shows you that reality has depths we're still exploring, mysteries we're still unraveling. Breathe slowly. Feel the weight of your body softening into stillness. Quantum entanglement is happening all around you, in the atoms of the air, in the photons streaming from distant stars, in the intricate molecular machines inside your cells. The universe is woven together by invisible threads of correlation, patterns written into the fabric of reality that connect each part to all the others. You're lying there in the darkness, but you're not alone. You're joined to everything that is part of the great quantum dance. Let this thought carry you gently toward sleep. The entanglement that mystified Einstein, that won Nobel Prizes, that's powering a new technological revolution, is the same entanglement that links you to the stars. In the quietest depths of nature, in the space between heartbeats, in the stillness before sleep, the quantum world continues its strange and beautiful dance. And you're part of it. Every particle in your body obeys quantum rules, exists in states described by wave functions, participates in the network of interactions that we're only beginning to map and understand. As you drift towards sleep, imagine the quantum field that underlies everything, a vast ocean of possibility from which particles and forces and matter itself emerge. This field fills all of space, connecting every point to every other point through quantum fluctuations and correlations. It's always there, beneath the surface of everyday reality, quietly determining what's possible and what's not, linking the micro to the macro, binding the universe into a single, coherent whole. In this field, entanglement is natural, perhaps even inevitable. When particles interact, they become part of each other's quantum stories. They share information in ways that persist even after they separate. The field remembers these interactions, encoded in phase relationships and correlation patterns that we're learning to read and manipulate. This quantum memory might be the deepest memory in the universe, more fundamental than biological memories or even the information stored in the cosmic microwave background. Rest well, sleepy scientist. The universe holds you in its quantum embrace. Somewhere, particles that were once part of ancient stars are now part of you. Somewhere, photons that left distant galaxies billions of years ago are arriving at Earth, carrying information about the deep past. Somewhere, entangled particles are spinning in perfect correlation across distances we can barely imagine. And you, lying there in the quiet darkness, are part of this vast, interconnected quantum reality. Good night.